short series of lectures. So now we're at lecture number 3. So today we will look at a concrete example, actually the first example which was proposed of a band theory that has bands with Chern numbers and therefore display a quantized Hall effect even in the absence of an applied magnetic field. Okay, so that's the plan for today. The next lecture will be on another model, Kane and Meller, which is an evolution of the model by Haldane. The ingredient that's added on top is the spin and the spin-orbit coupling. And then you will see that these guys were smart enough to invent a model in which you don't need to have an externally applied magnetic field, as in Haldane, but you don't even need to break time reversal symmetry to obtain an interesting effect. It will not be a quantized Hall effect, because if you don't break time reversal symmetry, Hall effect is 0. But still, there is some robustness in edge states appearing in this model. And this is a first example of what is now called a symmetry-protected topological state. Okay, and here are things that I realized I forgot to mention and which I should have done the last time. And I think it's important that I mention it because probably those are logical steps that were missing. So one important thing that I didn't stress is that the Berry type of effects or the emergent gauge field, it appears only when you try to do something to the electron, when you try to drive it by some external field or some force. And when you try to do this, that's where you see the importance of working with the Bloch Hamiltonian instead of the bare Hamiltonian, just the Hamiltonian. This is because there is a relation between the Hamiltonian in the presence of the external field and the Hamiltonian without the external field, but not the bare Hamiltonian, but the Bloch Hamiltonian. So I show you a concrete example. If you want to see what's the effect of applying constant force or an electric field on the electron, you can show that in the scalar gauge, so if you choose the scalar gauge to describe the electric field, your Hamiltonian is time dependent. And this Hamiltonian with the force, it's exactly equal to the Hamiltonian without the force. So that's just the band Hamiltonian. But the Bloch Hamiltonian, the one where you perform the unitary transform, and not with an arbitrary k, but a k that goes linear in time. So that's the reason why you remember for the Berry phase, I started speaking of a Hamiltonian dependent on a parameter and making a closed path with this parameter. But that's actually what a force does. If you apply a force and you have a joystick to vary the force, you can perform a loop in parameter space, and the loop goes linear in time. Okay? And two other things that I didn't mention. There are symmetry properties that imply some stuff on the Berry curvature. If you have time reversal symmetry, the Berry curvature, it's an odd function of the momentum, and therefore its integral over the full Brillouin zone, which is the Chern number, is 0. So if you have a band theory that respects time reversal symmetry, you will never get a Chern number and you will never get a quantized Hall effect. If you just have inversion symmetry instead, then the Berry curvature is an even function of k, and then it's not forbidden to have a non-zero Chern number. If you have both of them, of course, then the Berry curvature vanishes everywhere in Brillouin zone, and then you're back to the classical or the standard Bloch and Pyers semi-classical equation without the anomalous terms. And the last thing that I wanted to mention is that one of the title of a little section was Bloch sub-bundle, and I didn't insist on why I stressed it's a sub-bundle and not a full bundle. The reason is the following, is that if you do the construction that I did, but you don't project on a restricted number of bands, but you include all bands, then you can show that this is also a fiber bundle. It's a fiber bundle where the fiber is a Hilbert space of size the number of bands. This fiber bundle, you can show it's always trivial. So the only way of having a non-trivial fiber bundle is because you are projecting on a subset of bands. So in my lectures, I was restricting to the case of a single band, but could be 2 band, 3 band, as many as you want, but it should be a subset of the full Hilbert space. Otherwise, the corresponding bundle, you can show it's always trivial. Okay, so these were things that I hope I should have said last time. Now I'm moving on to this subject. So the first thing I want to do is to start from the quantum Hall effect, the usual way with the applied perpendicular magnetic field, and then show you how you can have a similar physics in a system which is still within the realm of band theory. So the quantum Hall effect, the usual context is the following. You have a 2D electron gas plus a perpendicular magnetic field, which is applied. And what is the experimental signature is that you look at the conductivity as a function of the magnetic field or as a function of the carrier density. You can do both. And you look both at the longitudinal conductivity and at the transverse conductivity. And the signal is the following. On the Hall conductivity, instead of having a straight line, as in the classical Hall effect, you start having plateaus. And at the same time, so this one is the Hall conductivity. And at the same time, in the longitudinal conductivity, instead of having something that is magnetic field independent as in classical physics, you start first seeing magnetic oscillation, Shubnikov-de Haas oscillation, and at some point those Shubnikov-de Haas oscillation, they become so big that when you have a plateau in the Hall resistance, you get a corresponding 0 in the longitudinal resistance. So it starts flat, the small oscillation, and then you get things like this. And when you go from one plateau to the next one, you have a spike, and then it goes again to 0 when you have a plateau, and then again a spike, etc. So the signature of the quantized Hall effect is a threefold. You should have plateaus in the Hall conductivity. You should have zeros in the longitudinal resistivity, and in addition, the plateaus in the Hall conductivity or resistivity are quantized. So here I just write for, they are all something like 1 over integer times the natural unit of resistance. So this was discovered by von Klitzing experimentally in 80, and it was a big surprise, and it took several years to understand the physics behind this effect. It came gradually, and actually, in my view, this is the birth of a topological insulator, in the sense that at level 0, all of topological insulators are descendant of the quantum Hall effect. It happens that in the original version, it seems crucial to have a magnetic field, but then as we gain understanding, and thanks to Haldane, he made clear that actually having an applied magnetic field is not crucial. What's crucial is to break time reversal symmetry, and even that, Kane and Melo showed, is not necessarily, because you can still get some interesting topological property without breaking time reversal symmetry. So the usual explanation for the quantum Hall effect is the following. It relies on having Landau levels. So actually, the usual starting point is to assume your 2D electron gas is in the continuum. You don't care about the band structure, or if you care, it's just by saying it's a Schrödinger equation with an effective mass, which is the band mass. But you don't really care about Brillouin zone, about bands having complicated shapes, and so on. You solve the problem of an electron in 2D in the continuum in presence of a perpendicular magnetic field, and you get an energy spectrum which is known as the Landau spectrum or Landau levels. And those levels, they are labeled by an integer n. And they are very degenerate. The degeneracy of a Landau level is given by the total flux across the system, so B times the total area of your 2D plane divided by the flux quantum. So it's a macroscopic degeneracy. If your system is infinite degeneracy for each Landau level. And so the Landau levels, if I represent them on an energy axis, they are usually drawn like this, separated by an energy which is the cyclotron energy. And here is the n equals 0, n equal 1, etc. And so now the quantum Hall effect, actually it was understood that it's some kind of band insulator, but where the bands are actually replaced by Landau levels. So now the next ingredient is to fill the levels. So band filling. Imagine that your Fermi energy is here. This is something like a band gap, except it's proportional to the magnetic field. And these levels are filled, completely filled, and the next one is empty. So you get a bulk insulator. You have something like a bulk insulator for certain fillings, and these fillings are usually written like this. Total number of electrons you compare with the total number of flux tubes, or here it's simply the total flux divided by the flux quantum. It's the number of flux tubes piercing the system. So when this filling factor is an integer, then this means, for example, here nu equal 2. This one is filled, and this one is empty. I just have enough electron to fill 2 Landau level, the next one is empty. Okay, so this looks like a band insulator, but you see that in this naive explanation, as soon as you add 1 electron, it will go there, and then it should be something like a metal, because this electron can be able to move, or if you remove 1 electron, you'll get a hole in here. Okay. But at the moment, I want to insist that it's a bulk insulator or bulk band insulator, except they are not real bands, but Landau levels. The main difference is that the bands are flat, and the number of states in a band is proportional to the magnetic field, and it's not proportional to the number of unit cells in the system. Okay, so that's the second ingredient, Pauli principle, the filling of electron into Landau level. So that's my first criterion to get a topological insulator. First, it's a bulk insulator. In addition, you already see it has an ingredient that it's characterized by some integer. So this could play the role of a topological invariant. I can say that this band insulator has a number which is 2. Or, yes, 2. So next I want to look at the edges. If I put the system on a ribbon, and for the quantum Hall effect, when you put your system not in an infinite plane, but you cut it in a ribbon, you have 2 edges. You can also solve the problem either exactly in some particular potential or semi-classically. But basically what you find is that now you can use this axis which labels the degeneracy within each level. You can use this as the dimension transverse to the ribbon. If I call this X and Y, and my ribbon is here, it has a width W. Basically now I can use this index as something which is roughly like X, and I have levels that when I'm far from 0 and from W, these are the bulk levels, but when you solve the Landau problem near the edge, the Landau levels, they bend like this. So here I'm doing something like a recap on that. I guess that you've all seen that, but I need to recap some things. And in particular, what you see is that because of this bending, if you have your Fermi level in a gap in the bulk, now this is no longer the case near the edges, because your Fermi level, now it's crossing this level near the edges. In addition, you can show, and here I'm just mentioning it, I'm not deriving it, that actually the slope of the bending, it gives the velocity of these modes. So these modes, they are no longer flat, they have a group velocity, they disperse, and those modes, they disperse with a positive velocity, those modes, they disperse with a negative velocity. So you imagine that those two modes, they go towards the blackboard, and those two modes, they move out of the blackboard. So you see now that we have something like a number in the bulk, it's 2, and this is related to the number of edge states that I have per edge. And in addition, those edge states, they are not standard 1D metals, but they are chiral 1D metals. Because on this edge, the edge states, they only move in one direction. On this edge, the edge states, they only move in the other direction. And those chiral edge states, because of this property, that the direction of motion is tied to the edge you're moving on, it means that you're immune to backscattering, because if you want to backscatter, you have that your impurity, it needs to send you to the other side of the sample. But the states associated with these chiral edge states, it's on the scale of the magnetic length, which is much smaller than the width of the sample usually. So if you have chiral edge states, let's say I only draw one on one edge and another one on the other edge, it's like having a 1D metal, two direction of propagation, but you've spatially separated them. And therefore, if you have an impurity here, it needs to connect to the other side to backscatter, but the edge state is exponentially localized on a scale given by the magnetic length, which is very small with the width of the sample, and therefore this probability is vanishingly small. And therefore you do not backscatter. So because it's chiral, it's immune to some disorder. And in addition, you see that on top of this bulk index, I can define an edge index, which is the number of chiral edge mode per edge. And so this was my second point for the definition of a topological insulator. It's a bulk insulator, but it's conducting on the edge, and it's not conducting in just conducting. It's conducting in a very particular manner. That means that it has some robustness to disorder. So here robustness comes from chirality, and you see that this is related to breaking of time reversal symmetry, because of course the edge state, they move in this direction because I applied the magnetic field like this. But if I reverse the magnetic field, then this edge will move down and this edge will move up. So the chirality is tied to the direction of the magnetic field, and this is the connection to breaking of time reversal symmetry. And the third point I mentioned for the definition of a topological insulator is that you have a property in the bulk, it's an insulator. You have a property on the edges, it's a conductor, a robust conductor, and those two things are related, which is known as the bulk edge correspondence. So the bulk edge correspondence here, it's trivial on this drawing. It's simply that if you field two Landau levels, you have two edge states, two chiral edge states per edge. If you field 3, you have 3, etc. So that's the bulk edge correspondence in this simple case. So here it takes this very simple form. The more general form is that actually you should compute the bulk index for this insulator, and then you have other insulator on the two other sides, which are just the vacuum. And the bulk edge correspondence, it's a relation between the number of edge states and the difference in the bulk indices. So something a little more correct is like this. Here it happens that the vacuum is a trivial insulator, therefore the bulk index here or here is 0. It's like having a metal that is completely empty. Yeah, you can imagine this. And therefore, the difference is simply given by the value of the bulk index here. Okay, and those three ingredients now I take as a definition of a topological insulator. And I want to show you that you can do this in band theory, not with Landau levels. So that's actually half of the title of Haldane's paper, Quantum Hall Effect without Landau levels. Okay, so let's go to the Haldane model. Yes, there is a possibility, but it's not backscattering because they move in the same direction. So you can change, but you're still moving in the same direction. Yeah. So backscattering is suppressed, but you can have scattering with the other modes moving in the same direction. Okay, so let's go. So that's the main part of the lecture. So we are playing with the Alden model introduced in '88, and this is a variation of the honeycomb tight binding model. So plus next nearest neighbor, that's the added ingredient. The simplest tight binding model is only with first neighbor. And the main ingredient is that you put phases on these hoppings to break time reversal symmetry. As you would do if you had applied a magnetic field. In a tight binding model, if you apply a magnetic field, your hopping amplitudes, they become complex number because they acquire a Peierls phase. But usually the Peierls phase is used to simulate a homogeneous magnetic field. Here, Haldane was smart enough to find a pattern of phases for the hoppings that do not kill the translation symmetry of the Hamiltonian. That's the main trick. The problem with the homogeneous magnetic field is that it's breaking translation symmetry of the Hamiltonian, even if classically the problem remains translation invariant when you have a homogeneous magnetic field. When you use, for example, the Landau gauge, the vector potential grows linearly in space, and therefore the Hamiltonian no longer commutes with the momentum operator. But you can introduce the equivalent of phases in a smart manner, such as to preserve the translation. You preserve your unit cell, it remains the same. Therefore, it will be a band model. You can use Bloch theorem, but you will break time reversal symmetry because you're introducing phases. And once you translate this into magnetic field, it actually means that you've created something like a very inhomogeneous magnetic field. Okay, so let's have a look at this model. So I'm trying to respect some convention that will be useful afterwards. So this is the Honeycomb Lattice. I identify two types of sites, A and B, black and white. There are two different atoms in the unit cell. Nearest neighbor vectors are called delta 1, delta 2, and delta 3. And then next nearest neighbor, so hopping from A to A or from B to B, are called B1 and minus B1. B2 here and minus B2. And this one is B3 and minus B3. So you have 3 first neighbors and 6 second neighbors. And the Bravais lattice vectors are those of a triangular lattice. So there are A1, for example, A1 equal minus B2 and A2 equal B1. So yeah, I took those two. This is A1, this is A2. It's within a unit cell, you need to take those two atoms. And you see the particularity of graphene is that the hopping in the simplest model is only between A atoms and B atoms. This is the reason for having a model in which the bands are coupled. If you have 2 atoms per unit cell, but you only use hoppings between A and only hoppings between B's, you still have 2 atoms per unit cell, but these are completely uncoupled bands. Okay, so the hopping amplitudes, they will be taken as follows. So T1 for the first neighbors, and we take it real and positive. And now the ingredient introduced by Alden is to take next nearest neighbor to be complex. So T2 is the name of the modulus, it's positive, and then I add phases, but I need to add phases in a smart way. So as to preserve, I want a pattern that I can make periodic with the unit cell. The unit cell is one of these hexagons, for example. So I need to do another drawing, otherwise we don't see anything. The other drawing is just to tell you whether the phase is E plus I phi or E minus I phi. So the pattern is as follows. So again, this is A, this is a B. And now, here, I put an arrow like this, meaning that this is a T2 EI plus phi. If I jump from here to here, in the direction of the arrow, I will put a plus. If I'm moving in the other direction, I will get a minus here. Yes. So the pattern is like this. In the triangle that I've drawn here, it's clockwise. Sorry? No, because the Hofstadter, it will break translation symmetry and it's no longer a band model. Here I want a band model without enlarging the unit cell. In the Hofstadter model, if you choose your flux to be a rational number P over Q, you get a unit cell which is Q times bigger. Here I do a pattern for an inhomogeneous magnetic field, but I always keep the same unit cell. That's why it remains a band spectrum. In the Hofstadter butterfly, when you vary infinitesimally the magnetic field, the pattern, the number of bands completely changes. In the Alden model, whatever phi, 2 bands. Yeah? Okay, for this triangle, I also move clockwise. So it seems pretty simple. Then you reproduce, you do it here again. Here again. Etc. So it's a periodic pattern by construction. But now if you wonder what does it mean in terms of magnetic field, you realize the following. I will identify 3 types of triangles. I have the triangles like this, close to the center of a hexagon. So I'm thinking maybe of this one. or I'm thinking of the other one. Those two, but what is important is that they move around the center of the hexagon. And those, they are like this. That's actually what I drawed. So it seems it's all there is. But now, see, something happens interesting if instead of having a triangle close, encircling the center of a hexagon, you're asking about a triangle that surrounds a site. So here is A, here is B again. So now I have a triangle around the B site. That's another type of triangle. It has a B inside, and now you see it moves counterclockwise. And same for a triangle around an A site. So for example, this is an A site, and if I look at the pattern, it moves counterclockwise. So what does it mean? It means that in these triangles, I have, let's say, a negative magnetic flux, BZ going towards the black bond, and here I have a positive magnetic field coming out of the black bond. Therefore, if I want to more or less tell you if you're an experimentalist and you like challenges and you want to apply an inhomogeneous magnetic field at the scale of a graphene hexagon, what you should do is that the inner part should be negative magnetic field, and the outer part here should be positive magnetic field. And then you should do this periodically. Yeah? So there is still a magnetic field in the story. That's how you break time reversal symmetry. But the trick is that you do it periodically. And now we will compute the energy spectrum and the wave function. I want to write the Bloch Hamiltonian for this model. So I need to erase something, but not everything. I want to keep the drawings. So I kept the convention in the original paper by Alden, which when I read it first, I thought it was completely obscure. I could not understand the word, and I thought it was very badly written. And in hindsight, I realized it's very well written, actually. So once you understand, you will see these are the same notation, so you should be able to read the paper. So now we can use Bloch theorem. It's a great help in the diagonalization because it tells us that we have a Hamiltonian which is block diagonal for each k value. And this block is simply a 2x2 matrix because we have 2 atoms per unit cell. So this block refers to hopping from A to A. This block refers from hopping from A to B, from B to A, and from B to B. Yeah. Actually, I said it wrong. If you're strict with quantum mechanics, actually the hopping term which is here is hopping from B to A. Yeah? Because you remember the matrix element, we read them like this. Okay, so let's look at this term, for example. So hopping from A to B. And I want to write the matrix element. So hopping from B to A, from A to B. So I start here and I want to reach B. I can do it like this, can do it like this, and I can do it like this. So this term, it reads as follows. It's T1, and then I get a phase for each jump depending on the vector. So this term is like this. It's the sum of 3 phases depending on the 3 first nearest neighbor vectors. So this is sometimes called a function f of k in the literature. In particular, the standard tight binding model for graphene is simply 0 here, 0 here, f here, and f star here. And that's it. Yeah? So that's a simple term. So AB is simply the complex conjugate. Then something more complicated, AA. So actually in the original model, Alden introduced two new terms. This one that is the main player, but he also introduced something which is more standard, which is a staggered on-site potential. So the staggered on-site potential, it's a description no longer of graphene. If you keep this and this, then this is a model for boron nitride, and it was introduced by Semenov in '84, and it's probably one of the first papers where there is a clear discussion of graphene or gapped graphene being related to the Dirac equation. So now on AA, I want to put, how can I go from A to A? Either I stay, and this is the staggered on-site, so I call it as Alden plus M. On BB, it will be minus M. And then I need to take into account all the other terms to jump from A to A, so I want to end up here. I can come from here, from here, from here, from here. I have 6 terms. And the only hard part is to get the sign correct for the phases. Yeah, so each time you look at the term, you jump from here to here. What is the vector? It's B3. And what is the phase? It's a minus because I go against the arrow. Okay, so I give you the answer here. It's plus T2 sum over J from 1 to 3, as here, of 2 cos K dot Bj plus phi. The reason is that I get 6 terms, and these 6 terms, they come 2 by 2 and they form cosine. So for example, we can check one of these phases. If I look at the B1, so this is this one, and I want to jump from here to here. I use the vector B1 and I go in the positive direction. Therefore, this term is T2E I phi with a plus, and the phase coming from the jump is like this. And now if I look at the other one, the one in front here, I want to jump, so I did the jump from here, so I jump from here to here. Now it's with a vector which is minus B1, but I'm also jumping against the arrow, so this second term is like this. And therefore the two of them, they build one of these cosines. And you get 3 cosines like this. Okay? And now for BB, it's very similar. The difference is that the staggered potential has a change of sign. That's what staggering means. I take the average to be 0 energy. One of the atoms has an orbital at plus m, the other one at minus m. And now, what's the change for this term? So when I move, I want to look at the similar term to this one. It's this one. I go from B to B, and I use the vector B1. But now you see I move against the arrow. So for the B to B, I get a minus here. And for the other one, the one here, the pattern now is like this. And now if I jump from here to here using the minus B1 vector, I get a phase which is a plus. So this one becomes like this. So basically the term for BB is the same as here. I just need to put a minus in front of phi. Phi controls the magnitude of the applied inhomogeneous magnetic field. Okay, so now we have the complete Hamiltonian. It's simply the sum. It's simply what's written here. But a nice way to discuss it, and now I need to erase that drawing at least, is to decompose it, because it's a 2 by 2 matrix. We want to decompose it on the Pauli matrices living in a sublattice space, so the space of A and B. So if I do this, it looks like this. H of k is 2t2 cos phi, sum over j from 1 to 3 of cos k dot bj times the unit matrix in AB subspace, plus T1 sum over j cos k dot delta j sigma 1 or sigma x, first Pauli matrix. I have a similar term but with a sinus for sigma y. And finally, I have a term for sigma z, which goes like m minus 2t2 sine phi sum over j sinus k dot bj sigma z. Yeah, so the only thing that I did is that I have the cos something plus something, and this is cos something minus sin something. That's how you separate this term from this term. Okay, and such a 2x2 Hamiltonian, the usual way to discuss it in the context of topological band theory is to introduce functions like this. I don't want to rewrite this expression each time, so I have a coefficient in front of the unit 2x2 matrix, and I also have a triplet of function or a vector with three components, hx, hy, hz, scalar, sigma, and this is hx, this is hy, and this is hz. And we will see that the crucial part is played by this guy, and this is mainly a spectator. Nothing happens much from this part. We will see that the part proportional to the unity, it changes the energy spectrum, but it doesn't do anything to the eigenvalues. Because it doesn't do anything to the eigenvalues, it doesn't change the u and k, and therefore all the geometrical quantities like Berry curvature, quantum metric, and so on, they are not affected by this guy. So actually, in the remaining of the discussion, I will do as if this guy was zero. Its only role is to break particle-hole symmetry of the energy spectrum, but it does nothing on the geometrical and topological properties. And this guy, I want to distinguish its modulus and its direction. So the modulus is a function of k, and the direction I call n. It's a unit vector that lives on the Bloch sphere. So from now on, I'm not discussing this term any longer. Okay, let's have a quick look at the symmetries of this Bloch Hamiltonian. Yes? No, T2 is real. It's the yeah. It's because I define it like this. So the hopping between next nearest neighbor, I call it modulus and a phase, which is either plus or minus. So this guy I took it positive if you want. Yeah, yeah. Okay, so let's have a look at the symmetries. So first thing to notice, if you put T2 to 0, this is graphene. So you know the energy spectrum. Qualitatively, it looks like this. Drawing it on a flat board, but I have two Dirac cones inequivalent in the unit cell. And the Brillouin zone, so the Brillouin zone is common to the graphene model and to the Haldane model. The Brillouin zone is a hexagon. Okay. There are only two ways to draw an hexagon, but I always get it wrong. So the Brillouin zone is like this. you get the reciprocal lattice vector of A1 and A2, and the center of the Brillouin zone is called gamma, and the corners of the hexagon, the inequivalent point, they are known as K and K prime, and the Dirac cones, they happen at near K and K prime. Okay, so that's this part of the Hamiltonian. If you put phi to 0, no phases, just T2, but as a real number, then you kill this term. And for the moment, I also put m to 0, but I keep the first term. So the first term, what it will do to the graphene bands is just that it will make it dissymmetric between positive and negative energy. So you will squeeze a little bit the valence band, and you will expand a little bit the conduction band. But otherwise, it's not very interesting term. If you kill T2, but you just put M, then you're doing boron nitride, which is sometimes called gapped graphene. It's the same as graphene, but the Dirac cones, they are gapped like this. And the gap is equal to 2m. So this is a boron nitride. So now the real new term introduced by Haldane is this guy. So what we want to study is the effect of this guy. Okay, what are the symmetries? So first, this Hamiltonian, does it have inversion symmetry? So to check that, you do the following. You apply inversion symmetry on the Bloch Hamiltonian, and inversion symmetry in the Honeycomb lattice, it's exchanging A and B sublattices because the inversion center is a midpoint between A and B. This is the reason for having sigma x. This is switching A and B. And you also need to switch by hand K to minus K. So is this a symmetry? The question is this equal to the original Hamiltonian? And the answer is no, because of this guy. Because of the M term. Because if I look at the M term, if I do, so I just look at the M term, it's like this, M times sigma z. If I change to minus k, nothing happens. If I encircle it between sigma x, this sigma z anti-commutes with sigma x, and I get minus m sigma z. So this is different from the original. But all other terms, they respect inversion symmetry. So the M term is here to break inversion symmetry. That's what happens already in boron nitride. Now, does this model have time reversal symmetry? So time reversal symmetry, I need to check what happens to the Hamiltonian after transformation by time reversal symmetry. Here it's very simple because I have spinless electron, so I do not have to play on spin. And the pseudo spin related to the sublattice, it's not a real spin. So time reversal symmetry does nothing on the A and B sublattice. So the only thing it does, K2 minus K, and because it's an anti-unitary operator, you get a complex conjugate. So does this term satisfy time reversal symmetry? Yes, they all do except this one. So why does this term break time reversal symmetry? So I just keep the part that I need. I have sine phi sine k dot bj and T2 that I took positive. So if I do the transformation, sine phi is not changed. Sometimes people are confused. They say if you inverse time reversal, you should flip the magnetic field or the inhomogeneous magnetic field. But phi here is not a dynamical variable in my problem. It's a parameter. So parameters are not acted upon by operators. Phi has the same status as T2. And T2, you would not act on it. So nothing happens to this, but, oh, sorry, I forgot something. It's sigma z. So it gets a minus here because it's minus k. And sigma z, it's actually a real Pauli matrix. So I can take the complex conjugate, but it's equal to itself. So now, because of this minus sign, this is different from the original term. So this one breaks time reversal, and this one breaks inversion symmetry. So this model is very nice because you start from graphene, which has both symmetries, and actually you can show that you need those two symmetries to have the Dirac cones, because in 2D you can show that band contacts are not stable in general. You need symmetry reason for stabilizing contact points in 2D. The symmetry reason in graphene is inversion and time reversal symmetry. And now you break one of them or the two of them, you immediately open a gap. If you break inversion symmetry, you realize boron nitride. We will see it turns out to be a trivial insulator. If you break time reversal symmetry, you realize a topological insulator or Chern insulator. Okay, so let's continue. Now, I want to do something to make the discussion simpler, which is instead of solving the full problem in the whole Brillouin zone, I want to concentrate in the low energy physics. So the low energy physics is in the vicinity of the Fermi level, which in undoped graphene is at 0 energy. So I want to concentrate on what happens near the Dirac cones, whether they are gapped or gapless. So what I'm doing now is working in this specific model, but it's not something that works all the time. Actually, one of the main messages of this lecture is that looking just at the spectrum, you don't get the full information. And thinking that you can concentrate in the vicinity of the Fermi level by having low energy effective theory is not always a good idea. We will see an example later on where in the spectrum you have the impression of having a single Dirac point, and if you would restrict to low energy physics, you would restrict to a single Dirac point, and if you do this, you get the result wrong. And actually, there are hidden Dirac points, so there are things that you need to keep that you don't see in the energy spectrum. You see it in the Hamiltonian or the wave function, but if you just look at the energy spectrum, you don't see it. Basically, if I sketch what will happen in the case that I want to show you, I will show you a case in which, in the Alden model, it's possible to choose parameters that have one gapless Dirac cone, and the other one is so gapped that the spectrum just looks pretty flat like this. So if you go to somebody, you bring this energy spectrum, you say my Fermi level is here, you want to do just the vicinity of the Fermi level, then you project just here, you compute your Chern number, or you compute your whole conductivity for this problem. So whole conductivity requires a gap, so you open a small gap here, you compute the whole conductivity, you will find a whole conductivity which is plus 1/2 or minus 1/2, which of course is not possible for non-interacting electron. There is a general result that the whole conductivity is always an integer in units of E²/h. And the reason is that you're forgetting about a second Dirac point, which is present. You see it in the wave functions or you see it in the Hamiltonian, but in the energy spectrum it has disappeared because it's so gapped that it just looks like it's not there. But the second Dirac point is always there. They always come in pairs. Okay, so we'll do this forbidden stuff, but in one case where it works. But be aware that projecting or looking at low energy physics is not always a good idea, and it should be double checked by performing a full computation in the whole Brillouin zone. Okay, so I'm at low energy. Now I want to go on a description which is a Dirac equation. So 2D massive Dirac equation. So the energy spectrum of the Hamiltonian we are just studying, it's very simple to diagonalize this Hamiltonian, actually the energy spectrum is just given by the modulus of h of k. So in the energy spectrum, only this part matters, and the vector that moves on the Bloch sphere does absolutely nothing. So if you look just at the energy spectrum, from the Hamiltonian, you've just extracted the information contained in the modulus, but you've lost all information contained in this object. Therefore, it means you have an infinity of models with different Hamiltonian, but having exactly the same energy spectrum. Yeah? So when you only look at the energy spectrum in a band problem, you're throwing away a lot of information, the one which is contained there, and that's where geometry and topology are in this business. Okay, so first imagine that I take m equals 0 and T2 equals 0. This is graphene, so I go quickly. You realize that, okay, so in such a case, Hz equals 0 and H0, actually I don't consider it, but it's also 0. And now I have two functions remaining, Hx in front of sigma x and Hy in front of sigma y. And I have these two functions, they are function of kx and ky. I have two independent functions that each of them depend on two independent parameters. So generically, there are solutions, there are values of kx and ky where those two coefficients there vanish. These are the Dirac points. But you see that they only exist because I had a symmetry reason. Here it's having inversion symmetry and time reversal symmetry that kill this guy and kill this guy. If you have those two symmetry, you don't have the sigma z term. And when you don't have the sigma z term, in order to have a contact between the two bands, in order to nullify the modulus here, you don't have to have three things vanishing, hx, hy, hz, which is not generically possible if you only have two variables, kx, ky. But here I have a symmetry reason for killing one term, and then with kx and ky I have enough freedom to kill the two other terms at specific points. So this is called a symmetry protected semi-metal. So it's only band contact provided there are some symmetry restrictions. Okay, so this is graphene. You can find the points where the gap vanishes. So these points are the corner of the Brillouin zone. You can take them here. Okay, so I took the wrong convention. This is K, and the K prime is also minus capital K. I take those two representative of the two inequivalent Dirac points. There are only two which are not related by a reciprocal lattice vector. If I now linearize the spectrum in the vicinity of these 2 points, plus capital K or minus capital K, I get an energy spectrum which is just a cone like this. I get two of them, one near K, one near minus K. And the Hamiltonian, you can also look at the Hamiltonian in the vicinity of those 2 points. And if you do this, it will look like this. H bar V plus minus Qx plus I Qy. So this is a name given to 3/2 T1 times A, which is the distance between nearest neighbor atoms, between A and B. So here you should, you have something like, yeah, sorry, there is no, I wrote the function f instead of what I wanted. This is sigma x and sigma y. And here actually you should recognize something like a Dirac Hamiltonian. So on the first day I quickly wrote the Dirac Hamiltonian. It's a Hamiltonian built on anti-commuting matrices. So the general structure is like this. And the matrices here, they have the property that they anti-commute and they should square to 1. So, and the number of matrices depends on the spatial dimension. So in D equal 3, you get 4 of these matrices. And to solve this algebra, this Clifford algebra, you need at least 4 by 4 matrices. But here we're in 2D. So in 2D, you actually only have 3 of these matrices. You have alpha x, alpha y, and beta. And in our case, alpha x is actually, in this case, either plus sigma x or minus sigma x, depending on the value. Alpha y is sigma y. And the third one is the third Pauli matrix. But it's absent here because we have the following parameter. C is actually called V. It's not the velocity of light, but it's the velocity of electrons in graphene. It's this number. And the mass is actually 0. This is the reason for saying that electrons in graphenes are massless. So, sorry? No, because it has to anti-commute with the other ones. Oh, sorry, I said alpha z. Yeah, here is beta actually. Sorry, thanks. Yeah, the matrices satisfying the Clifford algebra, it's never the identity. So this one is actually absent. You don't see it in the Hamiltonian. But you see that if you want to gap graphene, you need that this third matrix appears. Because in order to gap graphene, you need a reason for not having all the 3 hx, hy, hz being 0 simultaneously. But we already know of 2 points in reciprocal space where hx and hy vanish. So if you want to have a gap there, you need that hz at plus k or minus k is non-zero. And if you do this, then instead of having just sigma x and sigma y, you will have a sigma z as well. Okay, so if this is a recap of graphene. Now I want to look at the case where I use the full Alden model. And in such a case, you can show that hz near the Dirac points is given by m minus 2t2 sine phi sum over j sine plus minus capital K dot bj. And this numerically gives m plus minus 3 square root of 3 t2 sine phi. So I will introduce the following notation. I introduce 2 masses, m plus, m minus, which I define as follow. It's m plus minus 3 square root of t2 sine phi. So now the linearized Hamiltonian near the 2 Dirac points for the Alden model, it's like that of graphene. Plus a mass term, a term that gap the Hamiltonian. So now I introduced a term like this. And you see that the very nice trick of Alden is that now having both on-site staggered potential and the second nearest neighbor with the phase, you have enough knobs to have 2 independent masses for the 2 Dirac cones. So it means you can close one and leave the other open. You can make one big, the other small. You can change the relative sign of the 2 masses and so on. And that's a playground which is wide enough to get non-zero Chern numbers. Okay, so is there something interesting contained in the unit vector n? I told you with the modulus of h you get the spectrum, but there should be interesting stuff in n as well. So the interesting stuff is actually Berry curvature, at least. So let's try to compute that. So instead of working with the Brillouin zone like this, I take an alternative Brillouin zone. I take it like this, simply like this. Yeah, should be a parallelogram or a rhombi. And now my two k and k prime points, they are well inside my Brillouin zone. And what I'm doing when I'm doing this kind of expansion, it means that instead of considering the full Brillouin zone, I only consider what happens here and what happens here, and I neglect what happens somewhere else. So why is it not dangerous in the present case? We want to compute the Berry curvature, because our aim is to show a non-zero Chern number somewhere in this phase diagram of the Alden model. How do we compute Chern number? In principle, we should compute the Berry curvature everywhere in the Brillouin zone, and then integrate this Berry curvature, which is like a magnetic flux, a magnetic field, to get the total flux across the Brillouin zone. But you remember the structure of the Berry curvature. It had a structure like a second-order perturbation theory with matrix element of the velocity operator like this, but it had another feature. It had a denominator like this. And this means that the Berry curvature, the size of the Berry curvature, it's controlled by the energy difference between the bands. But we only have two bands. We have gapped our two Dirac cones. Because I removed the H0 term, I have an energy spectrum which is symmetric between positive and negative energy. And if I assume that my gaps are not too big, so I should have something like this, and maybe the other one is different, but is not too big either, something like this, then because of this factor, I know that the important contribution of the Berry curvature, they will come from regions where the gap is small. So that's the reason for saying all the main contribution is coming from those two guys. So it means that to compute the Chern number, I will do the following approximation. I will assume that the Berry curvature is 0 everywhere in Brillouin zone, except close to k and close to k prime. And this is valid here because I'm able to check by a full calculation in the full Brillouin zone, and I see that I only get mountains and valleys of Berry curvature near k and k prime. But in principle, it's not always valid. So let's do a calculation using the Dirac Hamiltonian. So I rewrite what I will use. I will use a Hamiltonian like this. Psi tells me plus minus whether I'm in valley k or valley k prime. Actually, when you only have the two Dirac cones in graphene without the mass term, the only difference between the two Dirac cones comes from the valley index, and this valley index, it changes what is known as the chirality of the Dirac cone, this sign. If you like the language of topological defects, if you look at the wave functions near k and near k prime, one corresponds to a vortex and the other one corresponds to an anti-vortex, and the sign of the charge of this vortex is tied to the sign of the valley. So now I'm putting h bar to 1, v to 1. I just want to keep the main information. And I have a mass in the Alden model that depends on the valley, m plus or m minus. See, I need to speed up a little bit. It's always when the hard calculation comes. Yeah, so let me just copy the main equations. the Hamiltonian, I can write it as the positive energy value. So this is just modulus of Q actually. And then I parameterize the n vector on the Bloch sphere in the usual way with two angles, theta and phi. So this is just a rewriting of the 2x2 matrix. No, sorry, this is actually not correct. It's Q plus the mass squared, yes. Cos theta is a new name for the quantity which is the mass divided by the positive energy spectrum. Sin theta is a new name for modulus of Q divided by the same energy. And EI phi is psi Qx plus I Qy divided by modulus of Q. This is actually the quantity, this angle phi is the quantity in which you see the vortex and the anti-vortex near the two valleys. Now that I have this notation, I can write the positive and the negative U eigenvectors. So I want to compute the Berry curvature for the lower band. This band, the minus band, this one is the plus band, because I imagine that I feel up to here, it's a band insulator. I want to know whether this band carries a Chern number or not, so I need to compute the Berry curvature for this band and then integrate to get the Chern number. So to compute the Berry curvature, I do step by step. I first compute the Berry connection. You remember it's U bra I grad U ket. This is the connection. It's equivalent to a vector potential. Take the curl. This gives me the Berry curvature, and then I integrate over the full Brillouin zone, which in my case will be restricted to small neighborhood here, small neighborhood here. Okay, so how is U minus? There is there is a choice. You remember it's the Berry gauge choice. So here is my choice for this calculation. You could have put the phase here, or half of the phase here and the other half here, or as you want. Each calculation will give a different Berry connection, but the Berry curvature, which is gauge independent, will be the same. It's one way to check that you didn't do mistakes. Okay, so the Berry connection, actually I'm writing the result for the two bands, but it's not useful. E grad Q U minus. Please check you're able to recover the following result, that it's plus 1 minus cos theta divided by 2 grad Q of phi. So you should be able, you inject this guy, compute its gradient with respect to Q, compute the bra, and then take the sandwich, and don't forget the I here, it should be real in the end. Then you compute the curvature by taking the curl. And here I obtain minus 1/2 grad Q of cos theta cross grad of phi, and it's always with respect to Q. But you remember that phi, it has this structure. So this is actually a vortex and an anti-vortex, depending on which valley I am in. So here it looks like the Berry curvature doesn't depend on the valley, but the valley index is actually hidden in phi. And so when you compute, when you use the value of cos theta and the value of phi, you will find that the Berry curvature, it's actually plus 1/2 psi, the mass at this direct point, divided by the energy spectrum to the power 3, in the z direction, in the unit z direction. So that's the Berry curvature. And you see the following. It's big when the energy is small, which means the gap is small because the spectrum is symmetric. So it's big here, and it's small in between. The other thing that you see is that it changes sign with the valley. So if the mass is the same in both valleys, you will have a compensation because it depends on the valley index when summing. So the trick of Haldane is to introduce a knob that allows you to have a mass that changes sign between the valley to compensate this change of sign and to obtain a finite Chern number. So the Chern number calculation for the negative band, the field band, is in principle I should integrate over the full Brillouin zone and divide by 2 pi. This gives me an integer. And here I make the approximation that I can replace that by a sum near each valley of an integral over Q that in principle I should cut because I want to stay in a small neighborhood. But this function decays so fast that it doesn't make much of a difference to actually integrate all over space. So actually, in the end, in order to integrate on this rhombi, I integrate on an infinite plane for this point, and again an infinite plane for that point. So that's the calculation we are doing now. And if you do this, you get the following. Sum over xi, 1 over 2 pi, that's here. 1/2 xi mass dependent on xi, coming from here. And then I need to integrate over Q, a quantity which is 1 over the energy spectrum. So this square root to the power 3. And actually, this is easy to perform. It gives 1 over the absolute value of the mass. So to do this, you need to go in polar coordinates. So the angle integral gives just 2 pi, and then you have just one integral between 0 and infinity on the modulus of Q, and you get an extra Q here coming from this two-dimensional integral. And then this you can find the primitive, and you can integrate, and you will find this result. So in the end, what is the Chern number for the valence band? It's like this. Sum over xi, 1/2 xi, and simply the sign of the mass, because I have a ratio between the mass and its modulus, and this is just the sign of the mass. So now you see that, imagine you're only using m, but you're not using T2 or phi. The mass at the two direct points, they have the same sign, because you remember that the mass is m plus minus 3 square root of 3 T2 sine phi. So it's the same mass, and therefore I have a compensation plus 1/2 minus 1/2. This is 0, so this is for boron nitride. But now I can do this for another part of the phase diagram. I can do it for the region where the mass has a different sign in the two valleys. How do you do this? You take, for example, m equals 0, but now you take non-zero T2, and you take a phi that maximally breaks time reversal symmetry, which is plus pi over 2 or minus pi over 2. Actually, there are two phases that do not break time reversal symmetry. It's phi equals 0 and phi equal pi, because in both cases, the hopping amplitudes, they are again real numbers. So the point in between is the one that maximally breaks. If you do this, you see that your mass at the two valley, it's plus in one valley, minus in the other one, and this change of sign, it compensates this one, and therefore here it gives plus 1/2, plus 1/2, So it gives +1. So let me now draw the phase diagram for the Alden model. Maybe I should have done this before. So there are two knobs. One that breaks time inversion symmetry, and I take it in dimensionless unit by using this as a normalization. But here, this direction breaks inversion symmetry. This direction breaks time reversal symmetry. And the phase diagram is the following. It looks like this. And here it's pi. Here it's minus pi. And the phase, it's actually on a circle. So this point is again the same as this one. And here it's 1. Here this point is graphene. It's not gapped. And those two lines, they are the lines where the mass in one valley vanishes. So on this line, for example, you have an energy spectrum that looks like this. And this was another interest of the Alden paper. He was trying to find a model in which you could beat the fact that Dirac fermions, they come in pairs. So he said, okay, I found a way. Here is a Dirac fermion, and I've lost the other one. But actually, you don't really lose the other one. As I told you, if you forget about this one, which is sometimes called spectator Dirac fermion, you get the whole conductivity wrong. Because the whole conductivity, as Taules, Komoto, Nightingale, and Dennis told us, it's simply E squared over H times the Chern number of all field bands, and the Chern number is always an integer. So the whole conductivity can only be an integer, or if you want, the Chern number can only be an integer. But if you forget one of the two Dirac cones here, each Dirac cone, whether it has a small gap or a big gap, it always contributes plus or minus a half. So there is a contradiction if you think that you are somewhere where you only have a single Dirac cone. Actually, you have two. One is gapless, the other one is gapped, but both of them, they contribute to the whole conductivity. Okay, so the equation for this line is m minus being equal to 0, and this line is m plus being equal to 0. Inside this zone, you have c minus equal 1. In here, you have c minus equal minus 1. And everywhere outside, it's c minus equals 0. So here is boron nitride, for example. This example. And the other one here, I was right in the middle here. And now if you like to study a phase transition between a Chern insulator and a trivial insulator, you can move along a line like this. At some point you encounter a phase transition which goes through a gap closing. The Chern number cannot change if the gap is not closing. So here the gap closes and you have a change of Chern number from 1 to 0, and it corresponds to the closing of a single gap for a Dirac fermion, and it's reopening but with a change in the sign. Because you have one Dirac point that changes the sign of its mass, its contribution to the Chern number changes from plus 1/2 to minus 1/2, and the change is an integer, is 1. So the fact that a single Dirac fermion contributes half integer is sometimes called a parity anomaly in this context. And it means that Dirac fermions, they always come in pairs, otherwise you violate the fact that the Chern number has to be an integer.
How do one move in the vertical direction experimentally? I see how one could move experimentally in this direction because this is changing T's, so pressure, for instance. But in this direction, I don't see how one can move the M value.
varying the staggered on site, it's probably it's via charge density wave or something like this. You would need something that produces a difference in energy on 2 sites. It could be a charge density wave that you describe in a mean field way. Otherwise, I don't see. But I mean, if you want to study the phase transition, you can also move this direction. Yeah. Yeah.
I see you can do pressure.
Yes. Okay. In the remaining nothing that remains. Okay, so I won't be able to do the calculation, so just let me give you the flavor. The last part was supposed to be on the Jakiv and Rebbe arguments and the bulk edge correspondence. So it's a concrete calculation that shows that if, so I will just do a drawing. It's a concrete calculation that shows you the following, that when you have a spatial boundary between a trivial and a non-trivial insulator, yeah, this is the boundary. Imagine here that I have positive m minus and negative m plus. We have just seen that this corresponds to having a Chern number which is +1 or -1, so here it's -1. And now imagine that I'm changing the sign of the second mass. Now I'm turning it to a value which is positive. So I have one way of describing the transition between a trivial insulator here and a Chern insulator is to imagine that you have a region where the masses in the two valleys are opposite. In the other case, they have the same sign. And you move continuously. And then the Jakiv and Rebbe argument is the following. They showed quite generically that if you take a Dirac equation in which the mass of the Dirac fermion depends on position, so now I imagine that this is position. If the mass depends on position and has a domain wall, because here if it's going from negative to positive, it means that the mass, it should look something like this. Then each time you have this, you have a special solution of your Dirac equation, which is a mid-gap state. So it's a state which is inside the bulk gap. So that's probably quite intuitive. If you want somewhere on the boundary, you're killing one of the mass and therefore you're closing the gap as a function of space. So you expect to have a mode which is gapless and tied to the domain wall, to the boundary. But the surprise and the interest of the Jakiv-Rebbe calculation is to show that this mode is chiral. So if you do this computation, so you can read it in the notes, you will see that you find a single mode and that this single mode is moving in this direction. And I don't draw it exactly on the boundary just to show it, but there is no meaning to drawing on the left rather than on the right. You can also show that this mid-gap state, it's localized exponentially near the boundary on a size which is given by the inverse mass. So something like h bar divided by m times v, where m is this guy. It's the asymptotic values here. Again. Okay, so I'm sorry I used too much time to explain that. It's a nice calculation, but the main message to remember from the Jakiv-Rebbe argument is the following. A domain wall, or more generally a defect in the mass of a Dirac equation, it produces a mid-gap state. And in addition, this mid-gap state, it acquires a property which is a chirality. So in one valley, you get a mode like this. In the other valley, you would get a mode like this. But here you see, to have a transition, in one valley, nothing happens. So in one valley, there is no domain wall. so the K prime valley, nothing happens, it remains gap. The gap closes in the plus valley, and I get only one mode on the edge, and in addition it's chiral. So this to show that even in this band theory context, you have the equivalent of the chiral edge modes of the quantum Hall effect. But you don't need the Landau levels to have these. And the last remark is that in this specific model, the Chern number seems to be either 0 or +1, but that's because of this specific model. It's easy to add longer range hoppings or more bands and to get Chern number which are as high as you want. Okay, so let's stop here.